Take a deep breath and settle into comfort. Tonight, we will drift through something extraordinary that surrounds you at this very moment, something ancient and gentle that fills every corner of space. You cannot see it with your eyes, and you cannot feel it with your skin, but it is there, flowing through the room where you rest, flowing through your body, flowing through everything that exists. It is the oldest light in the universe, cooled and stretched and softened over billions of years into a whisper of warmth. Imagine for a moment that the universe has a memory. Imagine at the very beginning of everything, the moment when all of space and time came into being, left behind an echo. Not a sound, but something even more fundamental. A glow. A radiation that has been traveling through expanding space for so long that it has become gentle, cool, almost like the fading warmth of embers after a fire has burned down to silence. This is the cosmic microwave background radiation, and it is everywhere. Right now, as you close your eyes and breathe slowly, this ancient light is passing through you. It has been traveling for nearly 14 billion years, crossing distances so vast that they reshape our understanding of what distance even means. And yet, despite this incredible journey, it arrives softly, carrying just the faintest hint of warmth, cooled by time and space to a temperature barely above absolute zero. Let me take you back to when this light began its journey. Picture a universe that is impossibly young, just 380,000 years after the moment of beginning. This might sound like a long time, but in cosmic terms, it is barely an instant. The universe at this moment is hot, so hot that matter itself cannot yet settle into the forms we know today. Everything exists as a thick soup of particles, electrons, and protons swirling together in a glowing fog that fills all of space. There are no stars yet. No galaxies. No planets or moons or any of the cosmic structures we see when we look up at the night sky. There is only this glowing plasma, this cosmic ocean of energy and particles, opaque and blazing with light that cannot yet travel freely. The light is trapped, bouncing endlessly from particle to particle, unable to stream through space because the universe is too dense, too hot, too crowded with matter for light to find a clear path. But the universe is expanding. It has been expanding since the very first moment, and as it expands, it cools. Slowly, gradually, the temperature drops. The fierce heat that keeps everything in a state of plasma begins to fade. And then, at a certain moment, something beautiful happens. The universe cools just enough that electrons and protons can finally come together to form the first atoms of hydrogen. The cosmic fog suddenly becomes transparent. This moment is called recombination, and it is when the light is finally set free. All at once, throughout the entire universe, photons that had been trapped for hundreds of thousands of years suddenly find themselves able to travel. They begin moving through space, streaming outward in all directions, carrying with them the image of that ancient moment when the universe first became transparent to light. These photons have been traveling ever since. And as they travel, the universe continues to expand around them. This expansion does something remarkable to the light. It stretches it. Just as a wave on the ocean can be stretched into a longer wavelength, the expansion of space itself stretches these photons, pulling them from visible light down through infrared, down into the realm of microwaves. The fierce glow of the early universe becomes a gentle warmth, cooled and softened by billions of years of cosmic expansion. Today, this ancient light fills the universe uniformly, coming at us from every direction. If you could see in microwave wavelengths, if your eyes were sensitive to this particular frequency of electromagnetic radiation, the entire sky would glow with a soft, even light. Not the light of stars or galaxies, but something older, something more fundamental. The afterglow of creation itself, cooled to a temperature of just 2.7 degrees above absolute zero. Think about what this means. Every point in space, no matter how empty it might seem, is bathed in this radiation. The vacuum between stars, the darkness between galaxies, the vast stretches of apparent nothingness that make up most of the universe, all of it glows faintly with this ancient light. You are floating in it now. Your bedroom, your body, the air you breathe, all of it is permeated by photons that have been traveling since before the first stars ignited. There is something deeply peaceful about this idea. The universe remembers its beginning. It carries that memory with it, imprinted in radiation that flows through everything. And that memory is not violent or chaotic. It has been gentle by time, cooled by expansion, transformed into something that exists at the very edge of warmth and cold, a subtle presence that connects every moment of now to the deepest past. Scientists discovered this radiation by accident in the early 1960s. Two researchers were testing a sensitive radio antenna, trying to eliminate sources of interference and noise. They kept detecting a persistent signal, a hiss of microwave radiation that seemed to come from everywhere at once. At first, they thought it might be interference from nearby cities, or perhaps something wrong with their equipment. They even cleaned out pigeons that had nested in the antenna, thinking the birds might somehow be the source of the noise. But the signal remained. Constant, uniform, coming from every direction. Eventually, they realized what they had found. This was not noise. This was the echo of the Big Bang itself, the cooled radiation from the moment when the universe became transparent. It was one of the most important discoveries in the history of science, confirmation that the universe had a beginning, that it has been expanding and cooling for billions of years, that everything we see around us emerged from that ancient, glowing plasma. The cosmic microwave background is remarkably uniform. In almost every direction you look, the temperature is the same, 2.7 Kelvin, just a tiny fraction of a degree above the coldest possible temperature. This uniformity tells us something beautiful about the early universe. It tells us that, at the moment this light was released, the universe was incredibly smooth and even, with matter and energy distributed almost perfectly throughout all of space. But not quite perfectly. There are tiny fluctuations in the temperature of this background radiation, variations of just a few millionths of a degree. These tiny differences are crucial. They represent the seeds of everything that came after. In the regions that were slightly denser, gravity had a tiny advantage. Over millions and billions of years, these small differences grew. Matter began to clump together, drawn by its own gravity, forming the first clouds of gas that would eventually collapse into the first stars. Those tiny temperature variations in the cosmic microwave background are like a map of the infant universe, showing us where galaxies would eventually form, where great clusters of stars would gather, where the cosmic web of structure that we see today would emerge. From nearly perfect uniformity, decorated with the faintest hints of variation, the entire rich complexity of the universe grew. When you look at images of the cosmic microwave background, you see what appears to be a model pattern of colors, like a soft, irregular glow covering the sky. These colors represent those tiny temperature differences, blown up and enhanced so we can see them. The pattern is both random and beautiful, like abstract art created by nature itself. And encoded in that pattern is information about the universe's age, its composition, its geometry, the seeds of every star and galaxy. This radiation has traveled so far. The photons you would detect if you had a microwave telescope have crossed nearly the entire observable universe to reach you. They began their journey when the universe was a tiny fraction of its current age, when everything was hot and dense and glowing. They have watched, in a sense, as space expanded around them, as the first stars formed and died, as galaxies coalesced from clouds of hydrogen, as billions of years of cosmic history unfolded. And they arrive here, now, at this moment, passing through your body at the speed of light, carrying their ancient message. About 400 photons from the cosmic microwave background pass through every cubic centimeter of space every second. Think about that as you rest. Hundreds of these ancient travelers are flowing through you right now, photons that are older than the Earth, older than the Sun, older than any star you could point to in the night sky. There is no drama to their arrival. They do not announce themselves. They simply exist, a constant background, a foundation upon which everything else is built. This is perhaps what makes the cosmic microwave background so perfectly suited for this quiet moment before sleep. It is not about explosions or collisions or cosmic violence. It is about the gentle persistence of light, the way energy can travel for billions of years and arrive softly, still carrying information, still connecting us to the deepest past. The temperature of this radiation tells us how much the universe has expanded. When the light was first released, the universe was about 1,000 times smaller than it is today. The photons at that moment had the temperature and wavelength of visible light, a bright orange glow filling all of space. But as the universe expanded, the light was stretched along with space itself. The wavelengths grew longer, the energy decreased, the temperature dropped. From a bright, hot glow to a cool microwave whisper. This process continues even now. The universe is still expanding, and the cosmic microwave background is still being stretched and cooled. In the far future, billions of years from now, this radiation will be even cooler, even more subtle. Eventually, it will fade to a temperature so close to absolute zero that it becomes nearly impossible to detect. The universe's memory of its bright beginning will become ever more faint, like a voice calling across an ever greater distance. But for now, in this era of cosmic history, the radiation is still detectable, still measurable, still teaching us about where we came from. It is a gift from the past, a message in a bottle thrown from the shores of the early universe and washing up on the beach of the present moment. And the message is simple. The universe had a beginning. It has evolved. It has cooled and expanded and given rise to structure and complexity. And underneath everything, connecting every point in space, is this ancient light. As you breathe slowly and let your muscles relax, you can think of yourself as floating in this ocean of ancient photons. They are not just around you but through you, passing endlessly from every direction, a gentle flux of energy that has seen more of space and time than any human ever will. They connect you to the earliest moments of cosmic history, making you part of a story that stretches back nearly 14 billion years. The cosmic microwave background is sometimes called the oldest light we can see. This is true, but it is also the youngest we will ever see from that era. The light from earlier moments is forever hidden from us because the universe was opaque before recombination. We cannot see the first few 100,000 years directly. The cosmic microwave background is like a surface, a last scattering surface, the place and time where light was finally free to travel through space. It is both the earliest moment we can observe and a veil beyond which we cannot directly see. This gives the radiation a quality of both revelation and mystery. It shows us so much, confirming our theories about the universe's age and evolution, providing a snapshot of cosmic conditions when the universe was incredibly young. But it also marks a boundary, reminding us that there are depths of time we cannot access, moments too early and too dense for light to escape and reach us. The cosmic microwave background is both answer and question, both window and wall. In the silence of space, this radiation spreads equally in all directions. It has no source that you can point to in the sky, no single location where it originates. Instead, it comes from everywhere, because it was released everywhere simultaneously. Every point in space was once part of that hot, dense plasma, and from every point, the light began its journey when the universe became transparent. The radiation you detect coming from one direction started its journey from a region that is now billions of light years away in that direction. The radiation coming from the opposite direction started from an equally distant region in the other direction. You are at the center of your own observable sphere of cosmic microwave background, and so is every other observer in the universe. This might sound strange at first, but it is simply a consequence of how space and time work on cosmic scales. The universe has no center, no edge. Every location can consider itself at the center of its own observable universe. And from every location, the cosmic microwave background appears the same, a uniform glow cooling slowly as the universe continues to expand. The radiation temperature is remarkably constant, not just across the sky but also across time. Measurements made decades apart show the same temperature, 2.7 Kelvin, with extraordinary precision. This stability is itself a message. It tells us that the expansion of the universe is smooth and consistent, that the laws of physics are reliable, that the cosmos operates according to principles we can understand and measure. There is comfort in this constancy. In a universe full of change, where stars are born and die, where galaxies collide and merge, where planets form and erode away, the cosmic microwave background remains steady. It cools gradually as space expands, but that cooling follows a predictable pattern. The radiation is a reference point, a cosmic standard, something that every observer everywhere can measure and find essentially the same. As you sink deeper into relaxation, let your mind rest on this image. The entire universe glowing softly with ancient light. No matter where you go, no matter how far you travel through space, you would find yourself bathed in this same gentle radiation. It is the ultimate common experience, shared by every point in the cosmos. A photon bath that connects all of space, making every location part of the same story, the same history, the same slow unfolding of cosmic time. The word microwave might conjure images of kitchen appliances, but cosmic microwaves are simply electromagnetic radiation with wavelengths between radio and infrared. They are longer than the waves of visible light, which means they carry less energy, feel cooler. The cosmic microwave background peaks at a wavelength of about 1 millimeter, which is firmly in the microwave part of the spectrum. This is why we cannot see it with our eyes, and why it took sensitive radio equipment to first detect it. Our senses are not tuned to perceive this ancient glow directly, but instruments can reveal it. Satellites have been launched specifically to map the cosmic microwave background in exquisite detail, measuring those tiny temperature variations across the entire sky. The data they collect is transformed into images, false color maps that show the structure of the infinite universe. These maps are among the most important scientific results of our time, providing a foundation for our understanding of cosmology, confirming theories about dark matter and dark energy, about the universe's age and composition and ultimate fate. Yet beyond all the science, beyond the measurements and the theories, there is something simply beautiful about the cosmic microwave background. It is proof that the universe remembers, that the past is not lost but transformed, carried forward in the form of cool radiation spreading through space. Every moment leaves its mark, inscribed in photons that continue to travel, to carry information, to connect what was with what is. As you prepare to let go of waking thoughts and drift towards sleep, you can hold this image gently in your mind. The universe filled with soft, invisible light. Ancient photons flowing through the darkness, through the walls of your room, through your body, connecting you to the deepest past. A warmth so faint it is almost cold, yet still there, still glowing, still carrying the memory of when everything began. This is the ancient warmth still glowing. Not a heat you can feel on your skin, but a presence that pervades all of space, touching everything equally, a cosmic background that underlies all other light, all other radiation. It is the oldest thing you will ever encounter, and yet it is renewed each moment as new photons from distant reaches of space arrive. It is both past and present, both distant and immediate, both mysterious and precisely measured. And it is eternal in its way. As long as the universe continues to expand, this radiation will continue to exist, cooling gradually, fading slowly, but always there, always connecting each moment to the moment of beginning. A gentle reminder that everything is part of one vast story, one cosmic evolution, one long journey from heat and density to the cool, expanded universe we inhabit now. Let this thought settle over you like a soft blanket. You are held in the embrace of ancient light. The universe itself surrounds you with its oldest glow. And in that glow, you can rest. The ancient light we just explored fills all of space with its cool, uniform glow. But there is another kind of radiation flowing through the cosmos, something more immediate, more dynamic, yet still gentle in its own way. Every star you have ever seen in the night sky is breathing. Not with lungs, not with air, but with streams of particles and waves of energy that flow outward constantly, endlessly, filling the space between worlds with invisible currents. Right now, even in the darkness of your room, you are being touched by the breath of our sun. Particles that left the sun's surface days ago are arriving at Earth, washing over the planet's magnetic field, some of them spiraling down toward the poles where they create soft glows of green and red in the polar skies. Photons of light that began their journey 8 minutes ago are passing through the atmosphere, reflected and scattered countless times, some of them finding their way to where you rest. The sun never stops giving. It never stops releasing energy into space, a constant exhalation that has continued for over 4.5 billion years. This stellar breath has a name. Scientists call it stellar wind, or solar wind when speaking specifically about our sun. It is a stream of charged particles, mostly electrons and protons, flowing away from the star at incredible speeds. But speed does not mean violence here. Think instead of a river, broad and deep, moving steadily through the landscape. The stellar wind flows like this, persistent and calm, carrying particles from the star's outer atmosphere out into the surrounding space, spreading them across millions and billions of miles. Our sun releases about 1 million tons of material into space every second through its solar wind. This might sound like a tremendous amount, and in human terms it is. But the sun is vast, containing more than 99% of all the mass in our solar system. Losing 1 million tons per second is barely noticeable. The sun has been breathing at this rate for billions of years and will continue for billions more, and it will barely diminish. It is a breath that can continue almost forever, sustained by the nuclear furnace burning deep in the star's core. Picture the sun's surface for a moment, not as a solid sphere but as a churning ocean of plasma, gas heated to such extreme temperatures that electrons are stripped from atoms, creating a sea of charged particles. This plasma is held to the sun by gravity, but it is also pushed outward by the tremendous energy produced in the core. Heat and pressure and magnetic fields all work together, and the result is that the outermost layers of the sun's atmosphere, the corona, are so hot and energetic that particles are constantly escaping, flowing away into space. These particles carry energy with them. They carry momentum. They carry the star's magnetic field, threaded through the flow like invisible lines extending outward from the sun. As the solar wind spreads through the solar system, it creates a bubble, a vast region of space dominated by the sun's influence. This bubble is called the heliosphere, and it extends far beyond the orbit of the outermost planets, reaching out into the space between stars. The heliosphere is where the solar wind eventually slows down, where it meets the thin gas that exists between stars, where the sun's breath mingles with the breath of other distant suns. This boundary is not sharp like the edge of a table. It is gradual, a region where one influence fades and another begins. But it exists, marking the extent of our star's exhalation, the reach of its invisible touch. All of this happens in silence. Space has nowhere to carry sound, so the solar wind makes no noise as it rushes past planets and moons and spacecraft. It is a quiet flow, detected only by instruments, felt only through its effects. Yet it is always there, streaming outward, filling the space between worlds with moving particles that connect everything in the solar system to the sun. Earth sits in this flow like a stone in a river. The solar wind rushes past at speeds of about 250 miles per second, sometimes faster during solar storms when the sun releases sudden bursts of energy. But most of the time, the flow is steady, predictable, a constant current that has swept past Earth for as long as our planet has existed. 4.5 billion years of solar breath, washing over the world, held away from the surface by Earth's magnetic field. That magnetic field is important. Earth is like a magnet, with its own invisible field extending out into space, creating a protective bubble called the magnetosphere. When solar wind particles encounter this magnetic barrier, they cannot simply pass through. Instead, they are deflected, guided around the planet, flowing past like water around a rock. The magnetosphere shields us from the constant bombardment of charged particles, creating a safe haven where life can exist without being harmed by the solar wind's energy. But some particles do find their way in, especially near the poles where the magnetic field lines curve down toward Earth's surface. These particles spiral along the field lines, diving into the upper atmosphere, colliding with molecules of gas. When they do, energy is released in the form of light. This is how auroras are born. The northern lights and southern lights are the visible signature of the solar wind interacting with Earth's magnetic field, a gentle display of glowing curtains and arcs dancing across the polar skies. If you have ever seen an aurora, you have witnessed the solar wind made visible. Those shimmering greens and reds and purples are the sun's breath-painting patterns in Earth's atmosphere, particles from the star's surface creating light hundreds or thousands of miles above the ground. It is one of the most beautiful phenomena in nature, and it happens because of this constant flow of energy and matter from our star. Other planets experience the solar wind differently. Mars has only a weak magnetic field, so the solar wind strips away its upper atmosphere over time, gradually eroding what was once a thicker blanket of air. Venus, with no magnetic field at all, feels the solar wind's pressure directly on its thick atmosphere. The giant planets, Jupiter and Saturn, have powerful magnetic fields that capture solar wind particles and create intense radiation belts around them, regions of space where trapped particles swirl in complicated patterns. Every world in the solar system exists within the sun's breath. Every asteroid, every comet, every grain of dust floating between planets is touched by the solar wind, pushed gently by its pressure, bathed in its flow. The solar system is not a collection of isolated objects separated by empty space. It is a unified system, connected by the star's constant exhalation, bound together by the flow of energy and particles that spreads outward from the sun to fill all the available space. And our sun is just one star. Every other star in the galaxy is doing the same thing, releasing its own stellar wind, creating its own bubble of influence in the surrounding space. Some stars breathe more gently than the sun, releasing less material at slower speeds. These are typically smaller, cooler stars, red dwarfs that burn their fuel slowly and steadily for trillions of years. Their stellar winds are weak, barely extending beyond their immediate neighborhood. Other stars breathe more violently, though even here we can find a kind of rhythm and pattern. Massive blue stars, dozens of times heavier than the sun, release stellar winds that are powerful and fast, carrying away so much material that these stars lose significant mass over their lifetimes. The wind from a massive star can travel at thousands of miles per second, carrying energy equivalent to millions of nuclear explosions. Yet even this happens continuously, steadily, a fierce breath that never pauses but also never varies wildly. Giant stars, stars that have swollen up after exhausting the hydrogen fuel in their cores, release dense, slow winds that carry away their outer layers over thousands or millions of years. These winds are rich in elements heavier than hydrogen and helium, elements forged in the star's interior through nuclear fusion. Carbon, nitrogen, oxygen, all the ingredients necessary for life, are carried away on stellar winds and spread through space, enriching the interstellar medium, seeding future generations of stars and planets. In this way, stellar winds are part of the great cosmic cycle. Stars gather matter from space when they form, condensing from clouds of gas and dust. They burn for millions or billions of years, fusing hydrogen into helium and heavier elements. And then they release that processed material back into space through stellar winds, through planetary nebulae when they shed their outer layers, through supernova explosions when the most massive stars die. The matter is recycled, used again to form new stars, new planets, new opportunities for complexity and structure. You are made of stardust, as the saying goes. But more specifically, you are made of matter that was once carried on stellar winds, breathed out by ancient stars, scattered through space, eventually collected into the cloud that formed our solar system. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of these elements were created in stars and released through stellar winds or stellar deaths. You are connected to stars not just poetically but literally, through the atoms in your body. The stellar wind carries more than just particles. It also carries energy in the form of electromagnetic radiation. Stars shine, pouring light into space in all directions. This light is another form of stellar breath, photons streaming away from the star's surface at the speed of light, spreading through space, warming anything they encounter. When sunlight touches your skin, you are feeling the energy of nuclear fusion happening 93 million miles away at the sun's core, transported to the surface and then released into space as light. Light from stars creates a gentle pressure called radiation pressure. Each photon carries a tiny amount of momentum, and when photons strike an object, they push on it ever so slightly. For small particles like dust grains, this pressure can be significant, enough to push them outward away from a star. Radiation pressure combines with stellar wind to clear space around stars, pushing dust and gas away, creating bubbles and shells in the interstellar medium. Comets display this effect beautifully. When a comet approaches the sun, its ice begins to vaporize, releasing gas and dust. The solar wind and sunlight push this material away from the comet, creating two tails. One tail, the ion tail, is pushed directly away from the sun by the solar wind, always pointing in the opposite direction from the star regardless of which way the comet is moving. The other tail, the dust tail, curves slightly, pushed by radiation pressure but also influenced by the comet's orbital motion. Together, these tails create the classic image of a comet, a glowing head with streaming tails, all shaped by the sun's breath and light. Even far from stars, in the spaces between solar systems, stellar winds have left their mark. The interstellar medium, the thin gas that fills the galaxy, is not uniform. It contains bubbles and shells and filaments, structures created by stellar winds and supernova explosions. Hot young stars blow bubbles in the surrounding gas, clearing out regions hundreds of light years across. When these stars eventually explode, they send shock waves through space that compress the interstellar medium, creating shells and triggering the formation of new stars. The galaxy is threaded through with the breath of stars, past and present. The space between stars is not empty but filled with material carried on stellar winds, enriched with heavy elements shaped by energy and pressure from countless stellar sources. This material will eventually form new stars, continuing the cycle. And those new stars will breathe too, releasing their own winds, adding to the flow of matter and energy through the galaxy. In clusters of stars, where hundreds or thousands of suns orbit close together, stellar winds from many sources mix and interact. The combined effect creates a hot, thin gas that fills the space between stars in the cluster. This gas glows faintly in X-rays, visible to space telescopes as a diffuse cloud surrounding the cluster. It is the collective breath of a stellar community, warmed by the energy of many stars, a shared atmosphere existing in the space between individual solar systems. Binary stars, two stars orbiting each other, create even more complex patterns. If one star is blowing a strong stellar wind and the other star is close enough, the wind from the first star can strike the second, creating a shock wave where the two stellar atmospheres collide. These collision regions can be hot and bright, visible as points of X-ray emission in the space between the two stars. It is like two gentle breaths meeting, and at the boundary where they meet, energy is released, pressure builds, creating a dynamic region that pulses with the orbital rhythm of the binary system. Some stars pulse naturally, expanding and contracting over periods of days or weeks or months. These pulsating stars breathe in a more literal sense, their stellar winds varying in strength as the star expands and contracts. When the star swells, its surface cools and more material can escape. When it contracts, the wind decreases. The result is a stellar wind that flows and pulses, creating shells of material that spread outward in concentric waves, like ripples on a pond. All of this happens at scales almost too large to comprehend. Stellar winds travel for years, decades, centuries before reaching the edges of solar systems. The heliosphere around our Sun extends about 11 billion miles from the Sun's center before it meets the interstellar medium. That distance is over 100 times the distance from Earth to the Sun, a span so vast that even light takes more than 16 hours to cross it. And that is just our Sun's breadth. Larger, more luminous stars create even more extensive bubbles. Yet despite these enormous distances, despite the vast scales involved, there is something intimate about stellar winds. They connect stars to their planets, stars to each other, stars to the interstellar medium. They ensure that nothing in space is truly isolated. Every star's breath mingles with its neighbors, creating a network of flows and currents that ties the galaxy together. In a very real sense, all stars are connected through their exhalations, through the particles and energy they release into space. As you rest now, breathing slowly and deeply, you can think about this cosmic respiration. Stars breathing out energy and matter, creating currents in space, touching everything around them with invisible streams of particles. Your own breath, the rise and fall of your chest, is an echo of this stellar process. You gather in air, extract what you need, release it back into the world, contributing your breath to the atmosphere that surrounds Earth. Stars do something similar on an unimaginably larger scale, but the principle is the same. Taking in energy through fusion, releasing it outward through radiation and stellar wind, maintaining themselves while also giving to their surroundings. There is a rhythm to it, a steadiness. The solar wind varies in speed and density, but it never stops. It flows continuously, day and night, summer and winter, year after year, millennium after millennium. This constancy is comforting. The sun has been breathing throughout all of human history, throughout all of Earth's history, providing energy for life, creating the heliosphere that shields us from cosmic radiation, connecting our world to the rest of the solar system through its gentle outflow of particles. Other forms of stellar radiation add to this picture. Stars emit light across the entire electromagnetic spectrum, from radio waves to gamma rays. Each type of radiation carries information about the star, about its temperature and composition and activity. Radio waves from stellar atmospheres, infrared from warm dust clouds around stars, visible light that paints the night sky, ultraviolet from hot stellar surfaces, X-rays from active regions and collisions, all of this energy spreads through space, traveling at light speed, filling the cosmos with signals and information. Imagine the galaxy as it would appear if you could see all these forms of radiation at once. The night sky would be ablaze with light, every star glowing not just in visible wavelengths but across the entire spectrum. The space between stars would shimmer with the combined radiation from billions of suns, a luminous fog filling the galaxy. The darkness that we perceive is only darkness to our eyes, which see just a narrow slice of the electromagnetic spectrum. In truth, space is filled with light, with energy, with the constant outpouring from stars. This energy has traveled so far to reach you. Light from distant stars has journeyed for years, decades, centuries, millennia. The nearest star beyond the Sun, Proxima Centauri, is about 25 trillion miles away. Light from Proxima Centauri takes over 4 years to reach Earth, meaning that when you look at that star, you are seeing it as it was 4 years in the past. Its current breath, the stellar wind and light it is releasing right now, is still in transit, traveling through space, and will not arrive here for another 4 years. For more distant stars, the light has traveled even longer. Stars hundreds of light years away, thousands of light years away, their light has been traveling since before you were born, since before nations rose and fell, since before written history began. And yet it still arrives, still reaches Earth, still adds its tiny contribution to the night sky. Each photon that enters your eye from a distant star has crossed vast reaches of space, navigated the interstellar medium, passed through Earth's atmosphere just to deliver its message of ancient starlight. In this way, stellar breath is also a form of communication. Stars are constantly sending out information about themselves, encoded in the light and particles they release. By studying this radiation, astronomers can determine a star's temperature, its composition, its age, its motion through space. The spectrum of starlight, the distribution of energy across different wavelengths, is like a fingerprint, unique to each star, revealing details about the nuclear processes happening deep in its core. And all of this happens naturally, effortlessly. Stars do not try to communicate. They simply exist, burning and shining, releasing energy as a natural consequence of their internal processes. The information we gather is a side effect, not a purpose. Yet it allows us to understand the universe, to learn about distant places we can never visit, to trace the history of stars from birth to death. The stellar breath that fills space also fills our minds with knowledge, connecting us to the cosmos in profound ways. As the night deepens and your body grows heavy with approaching sleep, let yourself float on this image. Stars breathing throughout the galaxy, each one releasing streams of energy and particles, creating currents in space that flow and mingle and touch everything. The sun breathing day and night, surrounding Earth with its heliosphere, warming the planet with its light, sending particles that create auroras at the poles. Distant stars breathing across the light years, their light traveling through space to reach your eyes when you look up at the night sky. You are held in this flow, this cosmic respiration, this endless exhalation of energy from billions of stars. The stellar breath passes through your room, through your body, connecting you to the sun and to all the other stars that shine in the darkness. And in this connection, in this shared existence within the galaxy's luminous atmosphere, you can find peace. The stars will continue breathing long after you fall asleep, long after you wake, long after your lifetime ends. They have been breathing for billions of years and will continue for billions more, a patience beyond human comprehension, a steadiness that anchors the galaxy. Let that steadiness hold you now as you drift toward rest, knowing that the universe is full of gentle, persistent flows, ancient rhythms that continue unchanged, stellar breath across the darkness, touching everything, connecting all. We have traveled from the ancient light that fills all of space, through the breath of distant stars, and now we arrive at something closer, something more immediate. Our own star, the sun, holds Earth in an embrace that is both invisible and essential. Right now, even in the darkness where you rest, even with your eyes closed and the world quiet around you, the sun's energy is reaching toward you, flowing across the emptiness of space, wrapping around the planet in ways you cannot see but that touch every moment of your existence. This embrace has been constant for as long as Earth has existed. 4.5 billion years ago, when our planet was nothing more than a ball of molten rock cooling slowly in the void, the sun was already shining, already sending its radiation outward, already touching the young world with warmth and light. Through all the ages that followed, through the formation of oceans and the emergence of life, through ice ages and warm periods, through the rise and fall of countless species, the sun has never stopped giving. Its radiation has washed over Earth every single day, a gift that arrives without pause, without condition, without end. The journey begins at the sun's core, 93 million miles away from where you lie. Deep in that core, under pressures and temperatures beyond anything we can create on Earth, hydrogen atoms are being fused into helium. This nuclear fusion releases tremendous amounts of energy that begins working its way outward through the sun's interior. The journey from core to surface takes a very long time. A single photon of energy might take tens of thousands or even hundreds of thousands of years to work its way from the core to the surface, bouncing randomly from atom to atom, absorbed and re-emitted countless times, gradually moving outward through the dense plasma that makes up the sun. But once that energy reaches the surface, everything changes. The photon is released into space, and from that moment, it travels freely. In the vacuum between sun and Earth, there is nothing to stop it, nothing to slow it down. It moves at the speed of light, covering the 93 million miles between star and planet in just 8 minutes and 20 seconds. 8 minutes from surface to Earth. 8 minutes for the warmth that will touch your skin, heat the ground beneath your feet, power the weather in the oceans and all the living things that depend on sunlight. Think about what this means. When you feel sunlight on your face, you are feeling energy that left the sun 8 minutes ago. The light you see shining through a window, reflecting off clouds, painting the sky in shades of blue, that light is 8 minutes old. The sun could stop shining right now, and we would not know for 8 minutes. We would continue to see it glowing in the sky, continue to feel its warmth, completely unaware that anything had changed. There is a gap in time, a delay between what the sun does and what we experience, a gentle reminder that even at the speed of light, space takes time to cross. But the sun does not stop shining. It continues, hour after hour, day after day, pouring energy into space. The amount is staggering. Every second, the sun releases energy equivalent to billions and billions of nuclear weapons. And this has been happening for billions of years, sustained by the vast reserves of hydrogen fuel in the sun's core. There is enough hydrogen remaining for the sun to continue shining at its current rate for another 5 billion years or more. The embrace that holds Earth is not temporary or fragile. It is enduring, powered by processes that will outlast anything humans might do, outlast entire geological epochs, outlast the rise and fall of continents. Most of this energy passes Earth by. The planet is small compared to the sun, and space is vast. Earth intercepts only a tiny fraction of the total energy the sun releases, less than 1/1000th of the sun's total output. But even that tiny fraction is enough. It is more than enough. The energy that reaches Earth drives our weather, powers the water cycle, enables photosynthesis, warms the oceans, melts ice, evaporates water, creates winds and storms and gentle breezes. Everything that moves on Earth's surface, everything alive, everything changing, is powered directly or indirectly by the sun's radiation. The radiation arrives in different forms, spread across the electromagnetic spectrum. Most of it is visible light, the light your eyes can see, the light that makes the world bright and colorful during the day. But there is also infrared radiation, which you feel as warmth, and ultraviolet radiation, invisible but energetic, the part of sunlight that can tan skin or cause sunburn if the exposure is too long. There are even small amounts of radio waves and X-rays, though these make up only a tiny portion of the total energy reaching Earth. All of this radiation travels through space as waves, oscillations and electric and magnetic fields that ripple outward from the sun at light speed. The waves need no medium to travel through. Unlike sound, which requires air or water or some material to carry it, electromagnetic radiation can cross the vacuum of space without difficulty. It is self-sustaining, electric fields creating magnetic fields creating electric fields in an endless cycle that propagates forward, carrying energy from star to planet across the emptiness. When this radiation reaches Earth, it encounters the atmosphere first. The atmosphere is thin, a delicate layer of gas clinging to the planet's surface by gravity, but it is crucial. It filters the incoming radiation, absorbing or scattering certain wavelengths while allowing others to pass through. Harmful ultraviolet radiation, the kind that would damage living cells, is mostly absorbed by ozone in the upper atmosphere. This protective layer, just a few molecules thick if you were to compress it to ground level pressure, shields the surface from the most dangerous frequencies of sunlight. The visible light passes through more easily, though even it is scattered by molecules of air. This scattering is what makes the sky blue. When sunlight enters the atmosphere, the shorter blue wavelengths are scattered in all directions more than the longer red wavelengths. You see this scattered blue light coming from all directions above you, creating the dome of blue sky that arches overhead during the day. It is a soft, diffuse light, gentler than the direct glare of the sun, spreading through the atmosphere and illuminating everything in a way that feels open and calm. At sunrise and sunset, when the sun is low on the horizon, the light must travel through more atmosphere to reach you. More of the blue light is scattered away, leaving the longer red and orange wavelengths to paint the sky in warm colors. These are among the most beautiful moments of the day, when the sun's embrace feels most visible, most tangible, as if the star itself is gently touching the edge of the world with color and warmth. The infrared radiation, the warmth, penetrates the atmosphere and heats the ground. Earth's surface absorbs this energy, warms up, and then re-radiates some of it back into space as its own infrared radiation. But certain gases in the atmosphere, water vapor and carbon dioxide and others, absorb this outgoing infrared radiation and trap some of the heat. This is the greenhouse effect, and it is what keeps Earth warm enough for liquid water and life. Without it, the planet would be frozen, too cold for the oceans and ecosystems we know. The sun's embrace is not just about the radiation that arrives, but also about how Earth's atmosphere holds onto some of that warmth, creating a balanced temperature that allows life to flourish. This balance has been maintained for millions of years, with only gradual changes as the atmosphere's composition shifts slowly over geological time. The sun shines, Earth receives the radiation, the atmosphere filters and traps it in just the right amounts, and the result is a planet that is neither too hot nor too cold, but suited for water in all its forms, ice and liquid and vapor, cycling endlessly through the environment. The energy that reaches the surface drives photosynthesis in plants, the process by which green leaves capture sunlight and use its energy to convert carbon dioxide and water into sugars and oxygen. This is the foundation of almost all life on Earth. Plants gather the sun's energy and store it in chemical form. Animals eat the plants, or eat other animals that ate plants, and all of them are ultimately living on captured sunlight, energy that traveled across 93 million miles of space to be transformed into the molecules that power muscles and nerves and thoughts. Even the food you ate today, the energy your body is using right now to keep you warm and breathing and alive, that energy came from the sun. If you ate plants, the connection is direct. If you ate meat, the connection goes back one step, to the plants the animal ate. If you ate fish, the connection traces through the ocean food web, through plankton that photosynthesized at the surface, capturing sunlight filtering down through water. Every calorie, every bit of energy in your body, is sunlight transformed and stored, chemical bonds holding the sun's radiation in a form you can use. The warmth you feel right now, the temperature of your body, the warmth of the blankets around you, these two are connected to the sun. Your body generates heat by breaking down food, by releasing the stored solar energy and using it to maintain your temperature. The air in your room was heated by sunlight during the day, either directly or indirectly through heating systems powered by electricity generated from fossil fuels, which are themselves ancient sunlight, energy captured by plants millions of years ago and stored underground until humans dug it up and burned it. Everything is connected to the sun's embrace. The weather outside, whether calm or stormy, is driven by uneven heating as sunlight strikes different parts of Earth's surface at different angles. The tropics receive more direct sunlight, heating up more than the poles. This temperature difference drives winds as air moves from hot regions to cold, and drives ocean currents that carry warm water toward the poles and cold water toward the equator. Hurricanes and thunderstorms are powered by the sun's energy stored in warm ocean water, released suddenly when that water evaporates and condenses into towering clouds. Even the gentlest breeze is a consequence of solar heating. Air warmed by the sun rises, cooler air flows in to replace it, and you feel this movement as wind. On a calm day, when just the faintest breath of air touches your skin, you are feeling the sun's influence made tangible, the star's energy transformed into motion, into a current that crosses your body for a moment before moving on. Water moves through the environment in an endless cycle powered entirely by the sun. The star's warmth evaporates water from oceans and lakes and rivers, turning liquid into invisible vapor that rises into the atmosphere. The vapor is carried by winds, concentrated into clouds, eventually condensing and falling as rain or snow. The water flows downhill, gathering into streams and rivers, returning to the ocean, and the cycle begins again. Every raindrop, every snowflake, every morning dew, All of it is part of this solar-powered circulation, the sun lifting water into the sky through evaporation and gravity pulling it back down, creating the flows and patterns that shape the landscape and sustain all terrestrial life. The sun's radiation also shapes the seasons, though in a subtle way. Earth's axis is tilted relative to its orbit around the sun. This means that during part of the year, the northern hemisphere is tilted toward the sun and receives more direct sunlight, creating summer. 6 months later, that same hemisphere is tilted away, receiving less direct light, creating winter. The total amount of energy Earth receives stays roughly the same throughout the year, but its distribution across the planet's surface changes, and this changing pattern creates the rhythm of seasons that is repeated for as long as Earth has had its tilted axis. You might be experiencing winter now, or summer, or one of the transitions between them. Whichever season surrounds you, it exists because of how Earth is positioned relative to the sun at this moment, because of the angle at which solar radiation strikes the ground where you are. In a few months, that angle will change, the seasons will shift, but the sun's embrace will continue unchanged, constant and reliable, the star indifferent to the seasons it creates, simply shining as it always has. There is something deeply peaceful about this constancy. The sun does not choose when to shine or how brightly. It simply exists in a state of equilibrium, gravity pulling inward balanced by pressure pushing outward, the result being a stable star that maintains roughly the same brightness year after year, century after century. The radiation that reaches Earth today is essentially identical to the radiation that reached Earth yesterday, and last year, and 1,000 years ago, and 1,000,000 years ago. There are small variations, tiny fluctuations in the sun's output linked to its 11-year activity cycle, but these are minor. The overall flow of energy is steady, dependable, a cosmic clock that keeps perfect time. This reliability has allowed life to evolve complex dependence on sunlight. Plants time their growth and flowering to the seasons, to the changing angle and duration of sunlight throughout the year. Animals migrate or hibernate based on the amount of daylight, responding to signals that are ultimately about the sun's position and the radiation reaching Earth's surface. Your own body has rhythms tied to sunlight, circadian cycles that regulate sleep and wakefulness, that influence mood and energy levels, all synchronized to the daily cycle of light and darkness created by Earth's rotation under the sun's constant gaze. Even now, as you rest in darkness, your body knows that the sun exists. It has internalized the rhythm of day and night, the pattern of light and dark that is repeated every 24 hours for as long as life has existed on land. Your brain produces melatonin in response to darkness, preparing you for sleep, a chemical signal that evolved because Earth rotates and the sun's light comes and goes with predictable regularity. The sun's embrace extends even into your biology, into the molecules and cycles that regulate your existence. Beyond the visible effects, beyond light and warmth, the sun's radiation creates the magnetosphere through a more subtle interaction. The solar wind, that stream of particles we explored earlier, carries the sun's magnetic field outward through space. When this field encounters Earth's own magnetic field, it compresses it on the day side, facing the sun, and stretches it into a long tail on the night side, away from the sun. The result is a teardrop-shaped bubble, the magnetosphere, that surrounds Earth and shields it from cosmic radiation and most of the solar wind's particles. Without this protection, Earth's atmosphere would slowly erode, stripped away by the solar wind and radiation over millions of years, the way Mars lost much of its atmosphere after its magnetic field weakened. The sun's embrace thus has two aspects. It provides the energy that sustains life, and it also poses a challenge that Earth's magnetic field helps mitigate. The relationship between Sun and Earth is not simply one of giving and receiving, but a more complex interaction where Earth must actively maintain its protective mechanisms while basking in the star's life-giving radiation. The particles that do penetrate the magnetosphere, spiraling down along magnetic field lines to create auroras, are a visible reminder of this ongoing interaction. The northern and southern lights are beautiful, but they are also evidence of the sun's power, the energy and particles constantly streaming outward, some of them finding their way past Earth's defenses to paint the polar skies with color. It is a gentle battle, if such a thing can exist, a continuous negotiation between the sun's outward pressure and Earth's magnetic resistance, creating a dynamic boundary that shimmers and shifts but holds. Satellites orbiting Earth must be designed to withstand the sun's radiation. Electronics can be damaged by energetic particles. Solar panels must balance the need to absorb sunlight for power against the degradation that radiation causes to their materials over time. Even the International Space Station, with its human crew, must monitor solar activity and take precautions during solar storms when bursts of radiation from the sun can reach dangerous levels for astronauts. The sun's embrace, so gentle and life-giving at Earth's surface, is harsher in the vacuum of space, unfiltered by atmosphere, presenting challenges that must be carefully managed. Yet for all these complexities, the fundamental relationship remains simple. The sun shines. Earth receives. Life emerges and persists in the narrow zone where temperature and radiation levels are just right. This has been true for billions of years, a partnership between star and planet that shows no sign of ending, that will continue for billions of years more until the sun finally exhausts its hydrogen fuel and begins to change in ways that will eventually make Earth uninhabitable. But that is so far in the future, so many billions of years away, that it feels almost like forever. For all practical purposes, for all of human history past and future, the sun's embrace is eternal. As you sink deeper into rest, you can hold this image gently. The sun shining across space, its light taking 8 minutes to reach Earth, arriving as a constant stream of energy that powers everything you see and feel and touch. The warmth that sustains you today, the light that illuminated your world, the food that gave you energy, the weather that moved through the sky, all of it flowing from that one star, from the nuclear fires burning at its core, transformed and transferred across emptiness to arrive here, where you are, where Earth floats in space wrapped in the sun's invisible embrace. The star will still be shining when you wake. It will shine tomorrow and the day after and for all the days to come. Its radiation will continue washing over Earth, gentle and persistent, warming and illuminating, sustaining the thin layer of life that clings to the planet's surface. You are held in this embrace now, even in darkness, even with the sun on the other side of Earth, because the atmosphere still holds the warmth from earlier, because your body still runs on energy that came from sunlight, because the entire system of Earth and life has been shaped by billions of years of receiving the sun's gifts. There is nothing you need to do. The sun's embrace asks nothing of you. It simply is, constant and unconditional, a flow of energy and warmth that will continue whether you think about it or not, whether you are awake or asleep, whether you are aware of it or completely absorbed in other thoughts. It is the foundation beneath everything, the source from which all other energy on Earth ultimately derives, the invisible connection that binds our world to the star at the center of the solar system. And in this knowledge, in this understanding of how deeply you are held by the sun's radiation, by the warmth that travels through emptiness to reach you, you can let go. Let go of thoughts, let go of the day's concerns, let go of everything except the gentle awareness that you exist within a vast system of energy and light, a system that has been operating since before you were born and will continue long after you are gone, a system that asks nothing and gives everything, the sun's invisible embrace surrounding Earth, surrounding you, holding all of us in its warm and patient light. We have explored the ancient light that fills the universe, the breath of stars flowing through space, and the embrace of our sun warming Earth. Now we turn our attention to something more mysterious, more energetic, yet equally patient in its journey. Throughout the galaxy, throughout all of space, individual particles are traveling at speeds that approach the ultimate limit, the speed of light itself. These particles move in silence, invisible, crossing distances that would take human spacecraft millions of years to traverse. They are called cosmic rays, though they are not rays of light but something more fundamental. They are matter in motion, pieces of atoms accelerated to extraordinary energies, wandering through the darkness like travelers on an endless journey. Right now, as you rest, cosmic rays are passing through your body. Every second, several of these high-energy particles strike every square inch of your skin, passing through you as if you were not there, as if your body were made of nothing more substantial than fog. Most of them continue downward, through the floor, through the ground, traveling until they collide with something or decay into other particles. You cannot feel them. They leave no sensation, no trace that you could perceive. Yet they are there, a constant rain of particles from space, a gentle bombardment that has continued for as long as Earth has existed. These particles come from far away. Some begin their journeys at the sun, accelerated by solar flares and other energetic events on our star's surface. But these are the least energetic cosmic rays, and they are stopped easily by Earth's atmosphere and magnetic field. The truly remarkable cosmic rays, the ones that carry the most energy and travel the farthest, come from beyond the solar system. They originate in places scattered throughout the galaxy, in the remnants of exploded stars, in the violent environments around black holes, in regions where matter and energy interact in ways that can accelerate individual particles to speeds that ordinary matter almost never achieves. Think about what it means for a single particle to carry enormous energy. A cosmic ray particle might be a proton, the nucleus of a hydrogen atom, the simplest and lightest atomic nucleus that exists. Normally, a proton is nearly motionless compared to the speed of light, moving at ordinary thermal speeds determined by temperature. But a cosmic ray proton has been accelerated, pushed by magnetic fields and shock waves and other cosmic processes until it is moving at 99% of light speed, or 99.9%, or even closer. At these speeds, the particle's energy becomes enormous, far more than its rest mass would suggest, energy borrowed from whatever process accelerated it, now carried through space as the particle races onward. The most energetic cosmic rays ever detected carry as much energy as a well-thrown baseball, all concentrated in a single subatomic particle millions of times smaller than a grain of sand. This is difficult to comprehend. A baseball has mass measured in ounces. A proton has mass measured in units so small they require special names, atomic mass units, each one representing less than a trillionth of an ounce. Yet through speed alone, through being accelerated to nearly light speed, that proton can carry the kinetic energy of a much larger, much heavier object moving at ordinary speeds. Where does this energy come from? The sources are varied, but many cosmic rays are born in supernova remnants, the expanding shells of gas and magnetic fields left behind when massive stars explode. When a star dies in a supernova, it releases more energy in a few seconds than the sun will produce over its entire 10 billion year lifetime. This energy drives a shock wave through space, a wall of compressed gas and magnetic fields expanding outward at thousands of miles per second. Particles caught in this shock wave can be accelerated, bouncing back and forth across the shock front, gaining energy with each crossing, eventually reaching speeds close to the speed of light. The process is called shock acceleration, and it is remarkably efficient. A small fraction of the supernova's energy goes into accelerating particles, but that is enough to create a population of cosmic rays that stream away from the remnant in all directions, joining the background of particles already filling the galaxy. Each supernova adds to this population, replenishing the cosmic rays that are gradually lost to the galaxy as some escape into intergalactic space and others collide with gas or dust. These accelerated particles then begin a journey that might last for millions of years. The galaxy is large, about 100,000 light-years across, and cosmic rays do not travel in straight lines. They are electrically charged, and the galaxy is filled with magnetic fields. Weak fields, far weaker than a refrigerator magnet, but spread across such vast distances that they influence everything charged that moves through them. A cosmic ray proton entering these fields is deflected, its path curved, sent spiraling around magnetic field lines in a complex dance that makes the particle's trajectory twist and turn. The result is that cosmic rays diffuse through the galaxy rather than streaming directly outward from their sources. They wander, bouncing from one magnetic irregularity to another, gradually spreading throughout the galactic disk and halo. A cosmic ray produced in a supernova on the far side of the galaxy might take millions of years to randomly walk its way to the solar system, its path so convoluted that if you could trace it, it would look like a tangled scribble filling a huge volume of space. Yet despite this wandering, cosmic rays too arrive here. They reach Earth from all directions, with no preferred source visible in the sky. The lower energy cosmic rays have been so thoroughly scrambled by magnetic fields that they arrive isotropically, meaning equally from all directions, their origins completely obscured by their long, twisted journeys. Only the highest energy cosmic rays, the ones with so much energy that even galactic magnetic fields barely deflect them, show any hint of directionality, any suggestion of where they came from. When a cosmic ray finally encounters Earth, it must first pass through the magnetosphere, just as solar wind particles do. Lower energy cosmic rays are deflected, turned away by Earth's magnetic field, never reaching the atmosphere. The planet is shielded, to some extent, from the full flux of galactic cosmic rays. But higher energy particles, moving fast enough and carrying enough momentum, can push through the magnetic field and enter the atmosphere. What happens next is a cascade. The atmosphere is thin compared to the solid Earth, but it is substantial compared to the emptiness of space. When a high-energy cosmic ray strikes an atom in the upper atmosphere, the collision produces a shower of secondary particles. The original cosmic ray might strike a nitrogen or oxygen nucleus, shattering it, creating pions and other exotic particles that themselves decay into muons and electrons and photons. These secondary particles spread outward in a cone, creating a cascade that multiplies as it descends through the atmosphere. By the time the cascade reaches ground level, a single cosmic ray might have produced thousands or even millions of secondary particles spread over an area of several acres. Most of these particles are absorbed or stopped before reaching the surface, but some make it through, especially the muons, which are relatively stable and penetrating. These muons are what you encounter, what passes through your body and continues downward. Each muon is a messenger from the original cosmic ray, carrying information about the high-energy collision that occurred miles above your head. This process happens constantly. Earth is bathed in cosmic rays from all directions, and at every moment, cascades are developing in the atmosphere, secondary particles raining down, muons passing through buildings and people and mountains. It is a gentle shower, energetic in the individual particles but spread out so diffusely that the total effect is small. You receive more radiation from natural sources in the ground and in your own body, from potassium and carbon isotopes, than you do from cosmic rays. The cosmic ray flux is simply part of the background, another form of radiation that life on Earth has adapted to over billions of years. Scientists study cosmic rays by detecting these secondary particles. Arrays of detectors spread across mountaintops or deserts can reconstruct the cascade, determining the energy and direction of the original cosmic ray from the pattern of secondary particles it creates. The highest energy cosmic rays produce cascades so large that detectors must be spread over hundreds of square miles to capture them. These ultra-high energy events are rare, perhaps 1 per square mile per century, but when they occur, they represent some of the most energetic individual particles in the universe. The origin of these ultra-high energy cosmic rays is still mysterious. They carry so much energy that it is difficult to imagine what could accelerate them. Supernova remnants, which work well for explaining lower energy cosmic rays, seem insufficient. The particles would lose energy too quickly, either by colliding with gas or by radiating it away, before they could reach such extreme speeds. Something more powerful is needed, and astronomers have proposed various exotic sources. Perhaps they come from the vicinity of supermassive black holes at the centers of galaxies, where matter falling inward creates enormous energies. Perhaps they are accelerated in the jets that shoot out from these black holes, narrow beams of plasma moving at nearly light speed. Or perhaps they come from even more distant sources, from outside our galaxy entirely. The highest energy cosmic rays might be able to travel in nearly straight lines across millions of light years, bridging the gaps between galaxies, arriving at the Milky Way from distant realms. If this is true, then cosmic rays connect not just stars within our galaxy but galaxies themselves, creating a network of particle traffic flowing through the universe at large. There is beauty in this uncertainty, in not knowing exactly where these particles come from or how they are accelerated. It means the universe still holds mysteries, still presents puzzles for future generations to solve. The cosmic rays continue their journeys regardless of whether we understand them, patient travelers carrying their energy across distances and times that dwarf human scales, eventually arriving here, adding their small contribution to the radiation environment that surrounds us. Cosmic rays also play a role in the galaxy's ecosystem. When they collide with interstellar gas, they ionize it, stripping electrons from atoms and creating charged particles. This ionization helps couple the gas to magnetic fields, allowing the fields to influence how the gas moves and collapses to form stars. Cosmic rays also heat the gas slightly, providing a source of energy that helps support clouds against gravitational collapse. In this way, cosmic rays influence star formation, though their effect is subtle, one of many factors that determine when and where new stars appear. They also produce some of the light elements found in the universe. Lithium, beryllium, and boron are rare, not produced in significant quantities by stars. Instead, they are created when cosmic rays collide with heavier elements like carbon and oxygen in interstellar space, breaking them apart through a process called spallation. The fragments are lighter elements, and over billions of years, cosmic ray collisions have built up the small abundances of these elements that we observe. Every lithium atom in the universe has a story involving cosmic rays, high-energy collisions in the depths of space, particles traveling for eons until they happen to strike just the right target. In a sense, cosmic rays are the galaxy's memory of violent events. Each particle is a fragment of energy released by a supernova or other energetic process, now wandering through space, a tiny piece of that ancient explosion still traveling, still carrying a portion of the energy that was released when a star died. The galaxy is filled with these memories, particles from countless supernovae over billions of years, all mixed together, creating a sea of high-energy particles that permeates the entire galactic volume. This sea is not uniform. Near sources like supernova remnants, the cosmic ray density is higher. In the spaces between spiral arms, where there are fewer stars and less activity, the density might be lower. But the differences are not dramatic. Cosmic rays have plenty of time to spread and mix, and the result is a fairly uniform background, a gentle hum of high-energy particles that exists everywhere, varying only slightly from place to place. Other galaxies have their own cosmic rays, their own populations of energetic particles wandering through their volumes. When galaxies collide, as they sometimes do over billions of years, their cosmic ray populations mix. The particles from one galaxy join those from another, creating a combined population that reflects the merged history of both systems. In this way, cosmic rays carry information not just about individual supernovae but about the larger scale evolution of galaxies, about collisions and interactions and the flow of matter on the largest scales. Some cosmic rays might be truly ancient, accelerated billions of years ago and still traveling, though this is difficult to confirm. High-energy particles can survive for a very long time if they do not collide with anything. In the low-density environment of intergalactic space, a cosmic ray might travel for billions of years without encountering enough matter to slow it down significantly. But in the galaxy, where gas and dust are more common, cosmic rays have shorter lifetimes, typically millions of years before they collide with something or escape the galaxy entirely. There is something meditative about imagining these particles, each one on its own journey, moving through the darkness and silence. They do not know where they are going. They have no awareness, no purpose. They simply exist in a state of motion, traveling at nearly the speed of light, carrying energy that will eventually be deposited somewhere, in a collision with gas or dust or atmosphere, the energy finally transferred and the particle's journey ending. But until that moment, the particle is free, a wanderer in space, tracing a path through magnetic fields and voids, passing between stars, crossing nebulae and empty regions, seeing nothing, feeling nothing, just existing in pure motion. There is a kind of peace in this, in movement without destination, in travel for its own sake, in the simple fact of continuing to move forward through whatever lies ahead. As you rest now, feeling your body settle and soften, you can think of yourself as similar to these particles, in a way. You too are moving through time, traveling from moment to moment, not knowing exactly where your path will lead but continuing nonetheless. The cosmic rays pass through you, and you pass through time, and both of you are part of the same universe, subject to the same fundamental laws, made of the same basic particles and forces, connected by the simple fact of existence. The cosmic rays do not struggle. They do not resist their deflection by magnetic fields. They simply respond to the forces acting on them, changing direction when pushed, continuing in a straight line when not, always following the path that physics dictates. There is no tension in their journey, no anxiety about destination. They are pure motion, pure energy, pure being. And perhaps there is something to learn from this, something about acceptance, about flowing with whatever comes, about not resisting the deflections and changes that life brings. The cosmic ray does not mourn its complicated path. It simply travels, and in traveling, it connects distant parts of the galaxy, carries energy from one place to another, participates in the great mixing and circulation of matter and energy that makes the universe dynamic rather than static. The galaxy would be different without cosmic rays. Colder, perhaps. Less ionized. Star formation would proceed differently. The chemical composition would be subtly altered. These high-energy particles, though individually tiny and seemingly insignificant, collectively shape the environment in which stars and planets form, in which life emerges. They are part of the web of cosmic processes that makes the universe what it is, another thread in the tapestry, another connection between past and present. Tonight, as sleep approaches, as your thoughts begin to drift and fragment, you can imagine joining the cosmic rays in their journey. Not literally, of course, but in spirit, in imagination. Letting go of control, of direction, of destination. Simply moving forward through darkness, trusting that the path will unfold, that forces beyond your control will guide you where you need to go. Not fighting, not struggling, just flowing, like a particle through space, silent and patient and endlessly traveling. The cosmic rays will continue their journeys while you sleep. They will pass through your dreaming body, through the walls of your room, through the earth below. They will arrive from distant supernovae, carrying energy released when stars died long before humans existed. They will scatter in the atmosphere, create cascades of secondary particles, add their small contribution to the background radiation that surrounds all life. And they will do this without fanfare, without announcement, simply being what they are, particles in motion, rivers of matter flowing through space, connecting the galaxy's past to its present, silent travelers in the endless night. Let that image hold you now. Rivers of particles, flowing through darkness, each one on its own path, all of them together creating a circulation, a movement, a dynamic quality to space that might otherwise seem empty and static. You are part of this flow, held within it, touched by it, connected to distant stars through the particles they send wandering through the galaxy. And in this connection, in this gentle bombardment of cosmic rays that you cannot feel, there is another reminder that you are not separate from the cosmos but woven into it, part of the same story, the same vast and patient unfolding of matter and energy through space and time. Rest now, and let the cosmic rays pass through you, silent messengers from the galaxy, carrying their energy from distant sources, traveling through the night, part of the endless circulation that makes the universe alive with motion and connection. They ask nothing of you. They simply pass by, and in passing, they connect you to everything, to the whole vast web of cosmic radiation that fills space, invisible but present, ancient but always arriving new, the rivers of particles flowing between worlds, through worlds, connecting all. We have traveled through ancient light, through stellar winds and solar embrace, through rivers of cosmic particles crossing the galaxy. Now we come to something that stands between Earth and all of these cosmic forces, something invisible yet essential, a shield that has protected our planet for billions of years. High above where you rest, extending tens of thousands of miles into space, Earth is wrapped in a bubble of magnetic force. You cannot see it, cannot touch it, cannot sense it in any direct way. Yet without it, life as we know it could not exist. This is the magnetosphere, Earth's invisible shield, a gentle barrier floating through the cosmic ocean, deflecting radiation, guiding particles, creating a safe haven where the planet can maintain its atmosphere and nurture the delicate chemistry of living things. The shield begins deep inside Earth, far below your feet, in the planet's core. There, nearly 4,000 miles beneath the surface, iron exists in a state unlike anything you encounter in daily life. The pressure is immense, millions of times greater than the pressure of the atmosphere at sea level. The temperature rivals the surface of the sun. Under these extreme conditions, iron behaves in strange ways, remaining liquid despite the crushing pressure, flowing in slow currents driven by heat rising from even deeper layers. This liquid iron is electrically conductive, and as it flows, it creates electric currents. These currents, in turn, generate magnetic fields. The process is called the geodynamo, a self-sustaining system where motion creates magnetism and magnetism influences motion, the two reinforcing each other in a cycle that has continued for billions of years. The result is that Earth behaves like a giant magnet, with a magnetic field extending far beyond its solid surface into the space around it. If you could see magnetic fields, Earth would appear surrounded by invisible lines of force, arcing from the South Pole to the North Pole, curving through space in graceful loops. Near the surface, these field lines are relatively straight, pointing roughly toward the magnetic poles. But farther out, they curve more dramatically, extending into space like the petals of a flower opening outward. This is the magnetosphere, the region where Earth's magnetic field is strong enough to influence the behavior of charged particles. The magnetosphere is not symmetrical. If Earth existed in isolation, surrounded only by empty space, the magnetic field would be evenly distributed, creating a simple pattern. But Earth does not exist in isolation. The sun is constantly breathing, sending out its solar wind, that stream of charged particles we explored earlier. This wind flows past Earth at hundreds of miles per second, and when it encounters the magnetosphere, it pushes against it, compresses it, reshapes it into something more complex. On the side facing the sun, the magnetosphere is compressed, squeezed by the pressure of the solar wind until the magnetic field boundary is only about 6 to 10 Earth radii away from the planet's center. This is about 40,000 to 60,000 miles, which sounds like a great distance, but in cosmic terms it is quite close. The solar wind presses against the magnetosphere like wind against a sail, creating a bow shock where the supersonic flow of particles slows down and heats up as it encounters the magnetic barrier. On the night side, away from the sun, the magnetosphere is stretched by the solar wind into a long tail that extends millions of miles downstream. This magnetotail reaches past the moon's orbit, creating a teardrop-shaped bubble with Earth near the front and a vast tail trailing behind. The shape changes constantly, flexing and rippling as variations in the solar wind pressure push harder or release, as gusts and lulls in the solar wind sweep past the planet. But the overall structure remains, a compressed dayside and an elongated nightside, a bubble being blown through space by the stellar wind. Inside this bubble, conditions are different from the surrounding space. The solar wind cannot penetrate directly. Its charged particles are deflected by the magnetic field, forced to flow around the magnetosphere rather than through it. Most of the solar wind simply passes by, rushing past Earth on both sides, continuing downstream toward the outer solar system. Earth sits in a quiet zone, a pocket of relative calm, shielded from the full force of the sun's particle stream. But some particles do find their way in, especially during times of high solar activity. The magnetosphere is not a perfect barrier. There are gaps and weak points, particularly near the poles where the magnetic field lines dive down toward Earth's surface. Particles can follow these field lines, spiraling along them, guided by the magnetic force toward the polar regions. As they descend into the atmosphere, colliding with molecules of gas, they create the auroras, those shimmering curtains of light that dance across the night sky in the far north and far south. Imagine these particles now, electrons and protons from the sun, trapped by Earth's magnetic field, spiraling downward along invisible lines of force. They are moving fast, carrying energy from their acceleration in the solar wind. As they plunge into the upper atmosphere, 60 to 200 miles above the surface, they collide with oxygen and nitrogen molecules. The collision transfers energy to these molecules, exciting them, lifting electrons to higher energy states. When the electrons fall back to their normal states, the energy is released as light. Oxygen molecules emit green light when struck by moderate energy particles, and red light when struck by lower energy particles at higher altitudes where the oxygen is less dense. Nitrogen produces blue and purple hues. The result is a display of color spreading across the sky, shifting and moving as the stream of particles varies, as the magnetic field lines ripple and dance in response to changing conditions in the magnetosphere. The aurora is both beautiful and informative, a visible manifestation of invisible processes, the magnetosphere made luminous through its interaction with the solar wind. People who live near the poles can watch these displays on clear nights, especially during periods of high solar activity. The lights appear as glowing arcs across the horizon, as vertical rays shooting upward, as pulsating patches that brighten and fade with a rhythm like slow breathing. Sometimes the aurora is faint, a subtle glow barely distinguishable from scattered city lights. Other times it is brilliant, painting half the sky in vivid greens and reds, moving so quickly that you can see the changes from moment to moment, curtains of light rippling as if blown by a cosmic wind. In a sense, they are blown by a wind, the solar wind interacting with the magnetosphere, transferring energy and particles to the system, creating disturbances that propagate through the magnetic field and eventually result in auroras. The lights are a message from the sun, carried by particles across 93 million miles of space, translated by Earth's magnetosphere into visible form, a greeting from one part of the solar system to another. But most of the time, for most of Earth's surface, the magnetosphere's protection is invisible. You do not see the solar wind being deflected. You do not feel the cosmic rays being turned away. The shield operates silently, continuously, requiring no maintenance and no awareness, simply existing as a consequence of the molten iron flowing deep below your feet. It is a gift from Earth's interior, a side effect of the planet's size and composition and thermal state, something that happened to arise early in Earth's history and has continued ever since. Not all planets have magnetospheres. Mars lost its magnetic field billions of years ago as its interior cooled and the convection driving the geodynamo ceased. Without this protection, the solar wind gradually stripped away much of Mars's atmosphere, eroding it over millions of years until only a thin remnant remained. Today Mars is cold and dry, its surface exposed to the full force of solar and cosmic radiation, its atmosphere too thin to support liquid water or shield any potential life from harmful particles. Venus, similar in size to Earth, also lacks a significant magnetic field. Its interior may be too hot, or may lack the right conditions for a geodynamo to operate. Whatever the reason, Venus has no magnetosphere, and the solar wind interacts directly with its thick atmosphere. The planet loses some atmospheric material to space, though its atmosphere is so dense that this loss is less catastrophic than on Mars. Still, Venus is inhospitable for other reasons, and the lack of magnetic protection is one more factor making it unsuitable for life as we know it. Earth, by chance or by necessity, has maintained its magnetic field throughout its history. The geodynamo has operated for at least 3.5 billion years, possibly longer. There have been times when the field weakened, or even reversed, swapping north and south magnetic poles. These reversals happen irregularly, every few 100,000 years on average, though the timing is unpredictable. During a reversal, the field does not disappear but becomes more complex and weaker for a period of perhaps a few thousand years before re-establishing with opposite polarity. Even during reversals, some magnetic field remains, and the atmosphere provides additional shielding from radiation. Life has survived multiple reversals without apparent mass extinctions. But the existence of a strong field most of the time has certainly been beneficial, helping Earth retain its atmosphere, reducing the radiation dose at the surface, creating stable conditions that allow life to flourish. The magnetosphere also shields Earth from galactic cosmic rays, those high-energy particles we explored in the previous section. Lower-energy cosmic rays are deflected by the magnetic field, never reaching the atmosphere. Higher-energy cosmic rays can penetrate, but their flux is reduced compared to what would reach Earth without the field. The planet sits in a partial shadow, magnetically speaking, with some cosmic radiation blocked and some allowed through, creating a radiation environment that is elevated compared to deep space but manageable for living organisms. You are protected by this invisible shield right now. Above your head, the magnetosphere extends into space, a bubble of magnetic force that has been there your entire life, that was there when your parents were born, when their parents were born, stretching back through all of human history and far beyond. Every human who has ever lived has lived under this protection, breathing air that was held to Earth partly because the magnetosphere prevented it from being stripped away by solar wind, shielded from radiation that would have made the surface far more hostile to life. There is something comforting about this, about being protected by forces you cannot see, by processes operating on scales too large and too subtle for direct perception. The magnetosphere asks nothing of you. It does not require your belief or your attention or your gratitude. It simply exists, a consequence of physics and geology, a byproduct of Earth's living interior, a shield that happens to surround the planet and, in surrounding it, makes life possible. The shape of the magnetosphere changes with the solar wind. During quiet periods, when the sun is calm and the solar wind is steady and slow, the magnetosphere is larger, more relaxed, extending farther into space. During solar storms, when the sun releases bursts of particles and energy, the magnetosphere is compressed, pushed closer to Earth, its boundary rattled by the increased pressure. Sometimes during major storms, the magnetosphere can be compressed so much that auroras become visible at lower latitudes, far from the poles, visible to people who normally never see them. These storms are a reminder that space weather exists, that the environment around Earth is not static but dynamic, responding to changes on the sun and in the solar wind. Satellites can be affected by these storms, their electronics damaged by surges of energetic particles, their orbits altered slightly by changes in the density of the upper atmosphere that heats and expands during magnetic storms. But on the ground, protected by atmosphere and distance, you feel nothing. The storms rage overhead in silence, invisible, their effects confined to technologies designed to operate in space or transmit signals through the magnetosphere. The magnetotail, that long extension of the magnetosphere on the night side, is a reservoir of energy and particles. During interactions with the solar wind, energy can be stored in the tail, building up over hours as the magnetic field is stretched and stressed. Eventually, the stored energy is released in a process called a substorm. magnetic field lines in the tail snap back toward Earth, accelerating particles, causing them to crash into the atmosphere and create intense auroras. The process repeats, a cycle of loading and release, giving the magnetosphere a kind of breathing rhythm, though on a timescale of hours rather than seconds. The Moon sometimes passes through Earth's magnetotail as it orbits. For a few days each month, the Moon finds itself inside the bubble created by Earth's magnetic field, shielded from the solar wind, experiencing a different radiation environment than it normally does. This has implications for future lunar exploration, as astronauts on the Moon would receive varying radiation doses depending on whether the Moon is inside or outside the magnetotail. Even at the Moon's distance, 240,000 miles away, Earth's magnetic influence can still be felt, a testament to the magnetosphere's size and reach. Other planets with magnetic fields have their own magnetospheres. Jupiter's is enormous, the largest structure in the solar system aside from the Sun's heliosphere. If you could see Jupiter's magnetosphere from Earth, it would appear larger than the full moon in the sky, despite being hundreds of millions of miles away. Jupiter's rapid rotation and powerful magnetic field create a magnetosphere that traps and accelerates particles to very high energies, creating intense radiation belts that would be lethal to unshielded spacecraft and humans. Saturn, Uranus, and Neptune also have magnetospheres, each shaped by the planet's rotation rate, magnetic field strength, and the environment it sits in. The gas giants have moons orbiting within their magnetospheres, and these moons interact with the magnetic field in complex ways. Jupiter's moon Io, for example, is volcanically active, spewing sulfur and oxygen into space. These materials are ionized and trapped by Jupiter's magnetic field, creating a torus of plasma around the planet, a glowing ring of charged particles that rotates with Jupiter. Earth's magnetosphere is more modest than Jupiter's but perfectly suited to Earth's needs. It is large enough to provide effective shielding, small enough that the Moon orbits outside it most of the time, complex enough to create beautiful auroras but stable enough that it has persisted for billions of years. It is a Goldilocks magnetosphere, not too strong, not too weak, but just right for a planet that harbors life. As you lie in the darkness, you can visualize this invisible bubble surrounding the planet. It extends high above, far higher than the atmosphere, far higher than any airplane or weather balloon has ever reached. Satellites orbit within it, some in low orbits just a few hundred miles up, others in higher orbits thousands of miles above the surface, all of them inside the protective bubble, all of them benefiting from reduced radiation compared to what they would experience outside the magnetosphere. The boundary between the magnetosphere and the solar wind is called the magnetopause, and it is a dynamic surface, constantly shifting and rippling as the solar wind pressure varies. Spacecraft have crossed this boundary, flying from the protected region inside the magnetosphere into the solar wind beyond, measuring the sudden change in conditions, the increase in particle flux, the shift in magnetic field direction. These measurements have allowed scientists to map the magnetosphere, to understand its structure and behavior, to predict how it responds to different solar wind conditions. There are regions within the magnetosphere where particles are trapped, spiraling back and forth along field lines, bouncing between the northern and southern hemispheres. These are the Van Allen radiation belts, named after their discoverer. There are two main belts, an inner belt starting about 600 miles above Earth's surface and an outer belt farther out. Spacecraft passing through these belts are exposed to high radiation levels and must be designed to withstand the exposure. But the belts also serve a purpose, trapping particles that might otherwise reach the atmosphere, concentrating them in regions away from Earth's surface. The magnetosphere is not just a shield but also a dynamic system, a laboratory where plasma physics plays out on enormous scales. Magnetic reconnection, a process where magnetic field lines break and reconnect in new configurations, happens regularly in the magnetotail and at the magnetopause. These reconnection events release energy, accelerate particles, drive currents through the system. They are part of what makes the magnetosphere active rather than static, a living system responding to external forcing. All of this complexity, all of this activity, happens above your head while you sleep. The magnetosphere does not rest. It continues its work through day and night, through all seasons, through calm and storm. It is patient, persistent, a tireless guardian created by the churning of molten iron thousands of miles below, maintained by the rotation and heat of the planet, shaped by the solar wind into a form that happens to be perfectly suited to protecting the fragile biosphere that clings to Earth's surface. In ancient times, people did not know about the magnetosphere. They saw auroras and wondered, creating myths and stories to explain the lights in the sky. Some cultures saw them as spirits dancing, others as reflections from distant oceans or fires, still others as signs and portents. The true explanation that these lights are created by particles from the sun interacting with Earth's magnetic field would have seemed like magic or fantasy. Yet it is real, and we can measure it, map it, understand it, even as it remains invisible to our eyes. You exist within this invisible protection, a bubble floating through space, carried along as Earth orbits the sun. The magnetosphere moves with the planet, maintaining its shape relative to the solar wind, always compressed on the sunward side, always stretched into a tail on the night side. You are inside this bubble now, safe from cosmic forces that would otherwise make the surface inhospitable, able to breathe air that the magnetosphere helps retain, able to live on a planet that the magnetosphere helps keep temperate and stable. There is no effort required from you to maintain this protection. The geodynamo operates independently of human activity, driven by heat from the planet's formation and from radioactive decay in the mantle. The magnetic field will continue as long as these heat sources persist, likely for billions of years into the future. Long after individual humans come and go, long after civilizations rise and fall, the magnetosphere will remain, faithfully performing its function, shielding Earth from the solar wind and cosmic radiation. As sleep draws nearer, as your breathing slows and deepens, let yourself feel held by this invisible shield. You are protected, cradled within a magnetic bubble, floating through the cosmic ocean in safety. Above you, the magnetosphere ripples and flexes, responding to the solar wind, creating auroras at the poles, deflecting particles, maintaining the boundary between Earth and space. And below you, deep in the planet's core, molten iron continues its slow circulation, generating the field that makes all of this possible. There is a symmetry here, a connection between the deepest interior and the farthest reaches of Earth's influence. The core creates the field extends into space, the field shapes the region around Earth, the region provides protection, the protection enables life, life includes you. A chain of cause and effect linking the center of the planet to your breathing body, all of it held together by magnetism, by invisible lines of force that curve through space in patterns too large to see but too important to ignore. Let this image settle over you like a blanket. Earth's invisible shield above, a gentle bubble of safety floating through the cosmic ocean, protecting all who dwell within. The magnetosphere asks nothing, gives everything, continues its patient work through eons. And you, resting in its embrace, can release your concerns, knowing that some forms of protection operate beyond your awareness, beyond your control, ancient and reliable, gifts from the planet itself. The shield will be there when you wake, unchanged, still performing its function. It will be there tomorrow and all the tomorrows after, a constant presence in an ever-changing universe. And in this constancy, in this reliable protection, you can find peace. Let go now and drift, held safely within Earth's invisible shield, the magnetosphere above, the solid ground below, and you between them, protected, cherished, part of the system that has nurtured life for billions of years and will continue long into the future. Rest in the bubble. Rest in the shield. Rest in the knowledge that you are held, safely floating through space, wrapped in invisible forces that deflect harm, that create beauty, that make this world a haven in the vastness. The magnetosphere surrounds you, and in its gentle embrace, you can sleep.